The first thing to take a look at is the polar carbon-leaving group bond. We're making carbocations in the first step of this reaction, and carbocations are unstable, or otherwise said, they're very high in energy. The alpha carbon, that's the carbon that's right next to the leaving group, is the one that's going to bear the positive charge. It will become the carbocation. The more stable the carbocation, the faster the reaction. Notice that tertiary carbocations lead to the fastest reactions. Secondary carbocations are next. Primary carbocations give very slow, or essentially no E1 reactions. What does tertiary mean? Tertiary means that the carbon in question is bound to 3 other groups that are not hydrogen. In this case, the carbon is bound to 3 R groups, making it tertiary. Secondary carbons are bound to 2 R groups. Primary are bound to 1 R group. One other type of carbocation that is relatively stable would be one that is resonance stabilized, such as the example I have drawn on the right. Resonance can also help to stabilize a carbocation. The next characteristic we're going to look at is the leaving group. This is the group that breaks away from the alpha carbon. A good leaving group is stable on its own. Good leaving groups are also weak bases because weak bases are stable. If you look at these two tables, tables 7.2 and 7.3, taken from Smith, these show good leaving groups and poor leaving groups for nucleophilic substitution, but these also apply to elimination reactions. Table 7.2 shows good leaving groups, and these include chloride, so chlorine bound to the carbon, bromide, iodide, and water. These are all weak bases, and their conjugate acids are very strong, so the conjugate acids have very low pKa values. These would work well for this type of reaction. Table 7.3 shows some examples of poor leaving groups, including fluoride, hydroxide, amide, hydride, and carbon-based nucleophiles. These are very bad leaving groups. Their conjugate acids are fairly weak, so they have higher pKa values. You will notice that the base and the solvent are not found in the rate equation, but they are nevertheless important to consider. Weak bases favor the E1 mechanism, and what we're going to see later is that if we have a strong base, the reaction will go by a different mechanism. To have an E1 type reaction, we're looking for a weak base, and often it is the solvent that will act as the base for the reaction. Polar protic solvents are the best, so an example might be ethanol. This is a polar molecule with an overall dipole toward the electronegative oxygen atom. Protic means there's a proton on the electronegative atom, or rather, a fairly acidic proton. Here we have an ethanol proton on the electronegative atom, so this is a polar protic solvent. Ethanol is one example, water is another example, etc. The solvent has the role of the base and has another role in the reaction as well. Polar protic solvents can stabilize the developing carbocation and the leaving group in the transition state. Remember that in the transition state, the leaving group is starting to break away. Its delta plus carbon is becoming a carbocation, and carbocations are unstable. What we find in the transition state structure is an interaction between the lone pair on the heteroatom, like oxygen, that I've drawn here, and the carbon. Negative attracts positive, which helps stabilize the developing positive charge. This can happen multiple times. The same thing happens with leaving groups, but this time the delta negative on the leaving group attracts the positive, the delta positive, of the proton in the solvent. Forming these hydrogen bonds helps to stabilize the leaving group as it leaves. The stabilization of this transition state lowers the transition state energy, which helps make the reaction go faster.